Hey everyone, this is Mukesh, and in this video, as part of my ongoing .NET on AWS series, we are going to learn about SQS or Amazon Simple Queue Service. We'll understand how it works under the hood, some key features and its use cases. We'll also be building a .NET application that can demonstrate a use case integrating SQS. So by the end of this video, you'll have a good working knowledge and understanding of Amazon SQS and how to use it to build robust and scalable .NET solutions. I would like to thank AWS for sponsoring this video and helping me produce more AWS content for the .NET community. If you are looking to get started with AWS, I have an entire playlist specifically for you. So here I teach everything you need to know about some pretty popular AWS services and various ways to get your .NET workloads deployed to the cloud. You can find these contents both on this channel as well as on my blog. To get notified whenever I post new content, consider subscribing to the YouTube channel and do not forget to hit the like button. Let's get started. First, let's understand what exactly Amazon SQS is. So SQS falls into the messaging service of AWS, which is a fully managed, serverless and scalable messaging service that can be used to build decoupled solutions and applications that largely rely on event-driven architecture. By introducing message queues, SQS facilitates communication between different components of an application, ensuring that all the tasks are executed asynchronously and effectively. SQS operates as a serverless service, meaning that you don't have to worry about provisioning or maintaining infrastructure. It can automatically scale to handle high volumes of messages and providing the reliability and availability needed for modern applications. It also ensures that messages are durably stored across multiple AWS availability zones, reducing the risk of data loss. And one of the standout features of Amazon SQS is its flexibility in handling different use cases. It offers standard queues, which provides nearly unlimited throughput with at least one message delivery. And FIFO queues, which is first in first out, which guarantee exactly one processing and strict messaging order. So these options make SQS suitable for everything from simple background job processing to critical workflows that demand precise execution orders. By leveraging Amazon SQS, the developers can decouple application components, improve the scalability, and enhance fault tolerance. This makes it an essential and crucial tool for building reliable cloud-native applications. So whether you're implementing microservice communication, handling background jobs, or managing workflows, SQS provides a robust solution for managing message queues effectively. Now, let's try to understand how Amazon SQS works. So Amazon SQS operates on a simple yet powerful concept. It basically enables communication between different parts of your application through messaging queues. So this is the concept. At its core, it basically decouples the message sender and the message receiver, allowing them to operate independently at their own pace and scale. The process begins when a producer sends a message to an SQS queue. So this message is stored in the queue where it waits until a consumer retrieves it. This decoupling ensures that the producer doesn't have to wait for the consumer to process the message, making the system far more efficient and scalable. Now, consumers can poll the queue to receive messages. Once a consumer retrieves a message, it is hidden from other consumers for a specific period of time, which is known as a visibility timeout. So during this timeout, the consumer processes the message. If the consumer is able to successfully process the message, it completes the task and it deletes the message from the queue. But if the consumer fails to process the message because of n number of reasons within the timeout, the message becomes visible again and can be retried by another consumer. It is also important to understand that multiple consumers cannot receive and process the same exact message from a given Amazon SQS queue. SQS ensures that each message is processed by only one consumer at a given time, even when there are multiple consumers connected to the same queue. SQS also allows a maximum message size of 256 KB. But if your messages exceed this limit, you can use a common workaround. That is, you can store the actual message content as an object in Amazon S3 bucket and include the bucket key or the URL within the SQS message. This approach allows your application to process large payloads by retrieving the full content from S3 whenever needed. While this method may seem like a workaround, it is a reliable and scalable solution for handling oversized message without hitting the SQS size limitation. Coming to the pricing, the Amazon SQS free tier provides up to 1 million free requests per month, making it an excellent starting point for most applications. For many, this generous limit is sufficient unless your application experiences significant traffic or becomes a viral sensation. So what's the best part? The Amazon SQS free tier isn't limited to just the first 12 months, it's free forever, giving you the freedom to explore and build with SQS without worrying about the upfront costs. But if your usage exceeds the free 1 million requests, additional calls are incredibly cost effective as well. They are priced at just $0.4 per million requests. This makes Amazon SQS a budget-friendly option for building reliable, scalable, decoupled solutions. To learn more about the pricing, you can check out the official pricing page of AWS. So now that we have understood some concepts, let's create a SQS queue via AWS Management Console to get a better understanding. Log into AWS Management Console and search for Amazon SQS and open it up. Here, let's click on Create Queue. Let's configure our queue now. So as mentioned earlier, SQS allows two types of queues. One is a standard, which has the maximum throughput but doesn't preserve the order of the messages. The other is a FIFO, which preserves the ordering and processes the message exactly once. You can make the choice based on your use case and requirements. For this demo, I'll be going with a standard queue. I will name the queue as demo. Now comes the configuration. So here are some key points to understand. First, the visibility timeout. This is the period in which once the message is read by the consumer, it gets locked from other consumer to read it. The default visibility timeout setting is 30 seconds. Next, we have the delivery delay, which is the amount of time to delay the first delivery of each message that is added to the queue. Any message that you send to the queue remains invisible for the consumers for the duration of this delivery period. Next comes the retention time. As the name suggests, it is the amount of time that a message that is not yet deleted gets retained. This can be up to 14 days. Then we have the receive message wait time, which is the maximum duration polling will wait for the messages to be available. Finally, we have the maximum message size, which can be anything between 1 KB to 256 KB that we have already discussed. Also, if you remember, we have also discussed a workaround that can bypass this particular limit. I'll keep everything as a default, which is the encryption and the access policies. Another important feature of the SQS queue is dead letter queue. It helps improve the readability of your messaging system by capturing messages that could not be delivered successfully. So these are essentially standard SQS queues that are designated to store messages that fail to process after a certain number of retries. So if I enable it, it'll be asking me for the queue, which will be any standard SQS queue and the maximum number of receives. So in distributed systems, there are scenarios where message processing can fail due to various reasons, such as a downstream service is not available, incorrect message format or schema, or application bugs or unexpected errors during the processing. So instead of losing these failed messages, SQS allows you to route them to a dead letter queue for later analysis and reprocessing. So when you create a SQS queue, you can configure a DL queue or a dead letter queue and specify the maximum number of receive attempts. This determines how many times SQS will attempt to deliver a message to a consumer before moving it to DL queue. So if the message fails to be processed successfully within the configured maximum re-attempts, it is moved to the DL queue. So the messages in the DL queue continue to remain there until you explicitly retrieve or delete them. You can monitor this particular DL queue to analyze why messages fails to process. This can help identify bugs, incorrect configurations, or unexpected scenarios. I will disable the DL queue for now. I'll keep everything as the default. Just recheck your configurations and click on Create Queue. So as you see, the queue demo is created successfully. You can actually send messages to this queue directly from AWS Management Console as well. So simply open up the send and receive messages. I will keep the message body as hello world and click on send messages. Now the concept is that the message is already sent, but we are not polling for the messages. So to start receiving the messages, you can click on poll for messages. As you see, it has read from the queue and you can also open this particular message. And here you go. We have the message that we sent recently. So I can also have the option to delete this particular message from the queue. I can click on delete, delete. So now that we are familiar with the basics and how to use it via AWS Management Console, let's jump into some .NET code. If you have made it this far in the video, don't forget to subscribe for more valuable content. For this demonstration, we'll be building a .NET solution and making use of Amazon SQS. Our solution will have two .NET 9 web APIs and a single class library. One API will be named as the producer, which essentially is responsible for producing event messages and placing the messages in the SQS queue. We will have another API that will have a background job that can poll this particular SQS for new message and process it. So note that the entire source code is available for free in my GitHub repository. Links are in the description. Now, the context of this .NET solution is that the producer API will have an endpoint that can register a new user. Once the user is registered, we want to send them a welcome email. So how do you achieve this? To do this, as soon as the user registration is done, we'll create a user registered event which will contain the metadata like username and email and place it in a SQS queue. The consumer API will now poll this particular SQS queue for new event messages. As soon as it receives the new event message, it decodes the message, does some kind of background processing and sends the email. And finally, it removes this message from the SQS queue. First up, let's create a message contract in the messaging library. So I'll open this up, right click, add a new class. I'll set it to an interface and let's name it iEvent. I'll make it public. And let me create a new class that is specific for the user registered event. So let's name it user registered event. I've already kept the code for this ready, so I'll just copy it there. As you can see, this particular user registered event has a user ID, the username and the email and the created date. It also has a constructor that accepts a user ID, username and the email, and the created date is automatically set to the current UTC. So once that is done, let me save it. So once that is done, let's install the required NuGet packages on both the APIs. So I'll just copy the commands. So I'll just enlarge this, select package manager console, and I will select the default project as producer API and paste in install package AWS SDK.SQS and the other required packages from AWS SDK. So once that is installed, I'll make sure that I get it installed on my consumer API as well. So I'll switch it. And let me run the commands again. So as you can see, we have installed the required packages. First, let's work on the producer API. So I'll create a new models folder. I'll hit on add, new folder, models, and create a new class that will basically hold the request for the registration endpoint. So I'll name it something like user registration command, and I'll create a new record for it that accepts a string username and a string email. So once that is done, I'll navigate to program.cs where I will have to first register the Amazon SQS client. So for this, I'll copy this thing over. So this basically registers the required AWS options as well as the AWS SQS endpoint. So basically, I don't have to do anything else for my .NET application to authenticate to my AWS account. It just happens magically. So to learn more about this, I have created a separate article and a video about this, for which I will leave a link in the description below. So now that section is completed. Let me copy over the registration minimal endpoint. So I'll add it somewhere over here. Let's resolve all the conflicts. I will add the references and the serializer. Let's go through this endpoint with a root at register where I have injected Amazon SQS iLogger configuration and it receives a body of user registration command. So once the client sends a request, we will validate the incoming request object and register a new user to the database. So let's assume that our registration operation has returned a particular user ID, which is a GUID. So once that is returned, we'll create a new registration event that we created earlier. So here, I'm going to pass the user ID that I generated now and the incoming username and the email. I will also assume that the name of the registered queue is user registered. So I will have it here. And once that is done, the next process is to get the particular queue URL from SQS. So we have the queue name, and using this particular command, we can get the queue URL from Amazon. So here what I have done is a try-catch block that can get the particular queue URL. So if the particular queue doesn't exist and throws a queue does not exist exception, I will go ahead and create a particular queue with the same name. And the queue URL variable will hold the URL of the queue. So once I have the queue URL ready, I'll create a SQS request. So in this SQS request, we are going to have the queue URL which we generated over here and also the message body which we are going to serialize from the event that we created earlier. So once that is done, I'm going to log this particular request, and after that, I'm going to use sqs.sendMessageAsync to send the particular request that I have created earlier. So once the request is done, I'm going to just return a particular OK or a 200 response from the API endpoint. Let's now work on the consumer API. So here, we'll first create a background service. I'll just add a new class that says user registered event consumer. So this is going to be a background service as I mentioned below. I am going to copy paste the code. So as you see here, this particular class or the background service is named as user registered event consumer, and it inherits from the background service, which again implements the execute async. So here I'm going to inject a SQS instance and a logger instance. So the first few lines of this particular service is going to be exactly same as the producer API. So it might be better if you find a way to share this particular code as there is some duplication. So since this is just a demonstration, I'm going to keep it very simple. So at the first, we have assumed a particular queue name that we have done the same in the producer as well. And we are going to log a message saying that I'm going to start polling a queue with the particular queue name. And finally, we are going to get the queue URL. This is the same exact function that you have seen in the producer as well. So we are going to generate a queue URL, which will be held at this particular variable. And we are going to create a receive request. So this is coming directly from the AWS SDK, where we pass a particular queue URL that we generated earlier. So once that is done, this is where the actual polling takes place. So inside this while loop, we are going to have an await SQS.receive message async and pass the receive request that we created here. Whenever the producer sends a message to the queue, the count of this particular polled message will be greater than 0. So it comes to this loop and we will be iterating through all the messages that is received in the queue. So here, I'm just going to log a message that says I have received this message from the queue with a body. So from here, you can do your custom processing like sending the email or decoding this particular message body into the class and anything else. So here I'm just going to add a 2-second delay just to mock event processing. And once the event is success, I can go ahead and delete this particular message. So that can be done by using the await SQS.delete messages async and passing the queue URL and the received handle of this particular message. So once that is done, the final step would be to register the AWS services within the consumer API. So let me copy that. I will go to the consumer API program.cs and somewhere over here, I can add this following. So this is going to be the same as what we have added in the service registration of the producer API. The only difference is that we have a background service. So to register the background service as a hosted service, we are going to add this particular line. So that's everything with the code. So we'll have to run both the consumer and the producer API. For this, right click on the solution, select configure startup project. I'll select multiple startup project. I will start producer API and also the consumer API. Click on apply and OK. So we'll be building this application, running it and testing it over Postman. I will now build and run the application. Let's build the application. And let me run it. So here I have the producer API that's up and running and also the consumer API. As you can see here, the queue user registered does not exist, so it creates. Now let me go back to my AWS management console. Click on queues and you can see that we have the user registered queue available now. Let's close this. I will now open up Postman. I'll keep everything side by side and I know that the producer API is running at port 7130 and we have our endpoint at the register. I have added this particular sample body and let me send the request. As expected, we are now seeing a log message that says publishing message to the queue user registered with the new body. And when you switch to the consumer, it says that it has received the message from the queue user registered and you can see the body is same. So this is how simple it can be to build a robust and scalable solution which is completely event driven. Now that we have explored Amazon SQS in detail, let's discuss some practical use cases where it shines in real world implementations. So one of the most common scenarios is integrating Amazon SQS with Amazon SNS. When an external system pushes messages or notification through Amazon SNS, you can have an SQS queue subscribe to this SNS topic. This setup adds a layer of fault tolerance to your system, ensuring that the messages are reliably stored even if the consumer service is temporarily unavailable. SQS also enables automatic retries, making it an excellent choice for resilient communication patterns in microservice architectures. It's a design that balances simplicity with reliability. Another great use case that I would say is managing background schedule jobs the same way that we did in this particular demonstration. So take a database backup for example. Imagine you need to trigger a backup every 24 hours. You can use a scheduler service to send a message to the SNS queue at the designated time. From there on, an AWS Lambda could consume the message and execute the backup process. This approach ensures that your backup jobs run consistently even if there are temporary issues with the scheduling service. This again adds a fail-safe mechanism to critical operations. These are just a couple of ways Amazon SQS can be leveraged in your systems. If you have other use cases in mind, share them in the comment section below. I would love to hear your thoughts and add them to the list. So that's a wrap for this video and I hope you found these insights helpful. In the next video, we'll discuss about Amazon SQS and explore how to integrate it seamlessly with the dotnet solution. We'll cover its core concepts, use cases and step-by-step demonstration to help you get started. Until then, keep learning and feel free to share your thoughts or questions in the comment. Don't forget to like, subscribe, and hit the notification bell so you don't miss the next video. See you soon.